Alright, so today we're going to be doing day 18 in Advent of Code. The first part of the challenge is that we get a long list of different numbers, and what these are actually coordinates, so row and column coordinates. And what we will do is we will add all of these coordinates to a map, and they're telling us that the actual grid from the actual problem we're supposed to solve is 70 by 70, but in this example it's just the last coordinate is 6 by 6, meaning that it's a 7 by 7 space. And what we do is we take these coordinates until some amount, so they're taking 12 of them, and they're adding them one by one to the grid, and they're adding hashtags. And we have to traverse from the top left to the bottom right, and we have to see, okay, and how many moves can we do this by not going through the hashtags? They're like walls, sort of like day 16. So we can see that this is the path that we would have taken, and it takes 22 steps with this example. So now what they want us to do is to simulate the first 1024 bytes, because these are supposedly bytes, and we add 1024 of them to the grid, and we see, okay, what's the minimum distance that we can travel to be able to get from the top left to the bottom right, from the start to the end. So to solve this, do I even have VS Code open? Apparently I closed it by accident. Let's see if it opens back to where it was. So to solve this, first we have to open the file and get all of the lines, of course, and then we make a final grid. And they say that the final grid is, the first coordinate is 0, 0 on the top left, and the last one is 70, 70, meaning that it's a 70 plus 1 by 70 plus 1 grid. So 71 and 71 for the rows and columns. Because if you start at 0 and you end at 10, let's say, then it's not 10 by 10, it's 11 by 11. So it's the same concept here. You always have to add one. Then what we do is we add the first 1024 memory locations, or whatever they want to call it, bits, and we see that we have 3400 of them, so we won't even be using all of them. So if I delete the last couple of rows, the first problem will still run perfectly, but presumably we're going to be needing it for part 2. And what we do is I get the coordinates, so whatever index we're at in the lines, and I take the 0th one and the first one after we split it with a comma, and I set it to X and Y, and maybe I should have set it to rows and columns, but it doesn't really matter. And yeah, I add a hashtag over here, and we can see that I do Y and then X, because the way that we constructed the grid here is in rows and columns. So we have to do it backwards if we're using X and Y. Then, if you remember day 16, it was something similar. We had to traverse a grid, and we had to go from the start to the end. But in this case, we know where the start is and we know where the end is, so we don't have to actually search for it. And to solve it, what we can do is we can do a breadth first search. So we've talked about this before. But basically we have different directions, so we have up, down, left and right, and we don't have any diagonals. If they specified that, then we would have to add this to the different directions that we're going into. If they said that we can jump like a horse in chess, then we would have to add that as well, but they didn't, so these are the only directions that we can actually travel in. Then I'm going to have a 2D list as well, just like we've done with the final grid, but for the distances, so that we know, okay, how much does it cost to get to that specific part in the grid. And we initialize it with -1 to know that, okay, we've never actually traveled to it and we don't know the distance yet. And then we initialize the first distance, the 0, 0 index with 0, of course, because there's we don't have to travel at all to get there, because that's the starting point. And I call start 0 and start 1, so the 0th index in start and the 1th index in start, so 0, 0. We could have just put 0, 0, it's the same thing. Then we use dq, which is a double-ended queue. I've imported it from collections. We imported dq, and it's just a bit more efficient than a regular queue, since we're going to be popping from the left and appending to the right, so it's just more efficient to have a double-ended queue, since it will be sort of traveling with it, and we don't have to scooch the items all the way to the beginning. If we remove an element on the first index, we don't have to move everything one by one until we get all the elements to the 0th index again. We can just have a double-ended queue, and it takes care of that for us, and it's better for the time complexity. So we implement the queue by saying while queue. So while there is something in the queue, we pop from the left what we found in the queue, and that is going to be the row and column. And if we somehow find that the row and column that we currently popped is the end, it means that we have reached the end, and we can just print the distance that we found in that specific place. So we print it, and that's how we get the answer, and then we can break from the while loop. But to be able to even get there, we have to go step by step. And how do we do that? Well, we do for each certain direction that we can take, so up, down, left, and right, we take the direction row and the direction column, and we add it to the current row and the current column to get a new row and a new column. And we check, okay, is it even in the grid space? So is it out of bounds? So this is what this is checking for the row. This is what this is checking for the column. And we have to check that it is not a hashtag where we're looking to traverse right now, because that's a wall and we can't go through it. And of course we have to check that we haven't visited it already, because why would we visit it twice? And we do that by checking if it's a -1, meaning that we haven't visited it yet. And then what we do is we add to the new place, we add the price of the old place, and by price I mean distance from the beginning, and then we add 1. So to whatever new place that we've visited. So if we are here and we're visiting here, if this place was costing 8, then we know that to traverse 1 more, it will cost 9 to get here. And then we append to the queue the new row and the new column. And notice that since there's a for loop, it will get at most 4 different directions appended to the queue. And since we start at the top left, actually, it's only possible to go to the right or down. The left and up will not even go in the if statement, because they are out of range. The new row and new column will be less than 0. So they will not actually append that. So it will only travel to the valid positions, and then we will be tracking the distance slowly as we travel towards the end and avoiding all the obstacles. If there was a hashtag here, then we should have gone around it somehow. And we find the cheapest place to get there, the cheapest way to get there. And we print the distance. So if we run the code, we see that we will get 454, I believe. Yeah, that was 454. So if we go to the website, that is the correct answer. So that was part 1. And now to solve part 2, the problem is that instead of just looking, okay, what's the fastest way to get there, what they actually want us to do is to be able to add more of the bits that we have in the list, and to see, okay, at what point have we added so many bits that we can't even traverse it at all from the beginning to the end. So we could see that before we could traverse it, but if we add 1 more bit, so let's assume that this is the next bit in line at this coordinate, if we add it here, then there's no possible way to get to the end now. So we have to say, okay, at what point is it no longer possible to get to the end? And they want us to answer in coordinates. So they want us to answer in, let's say, 6, 1. They don't want us to say, okay, which index in the bytes coordinates it was. They want us to say what coordinates it was exactly. So to do that, we of course read all the lines again, and we store all of the bytes to fall. Instead of doing it just for the first 1024, storing them, we actually store all of them now. And we store it in a variable called bytes to fall. And then we have the final grid again, the start and end as we had before. And what we can do is we can make a binary search to be able to find the point where it is no longer possible to find the end. And how do we know if it's possible to get to the end? Well, I've made a function isPathPossible, which I'll be showing in a second. But let me explain binary search real quick. So if we're trying to traverse it step by step, then at worst case, it will take n, because if the place is right here, at worst case, we will be having to traverse 1 by 1 all the way to the end. So if there's n elements, it will take n amount of steps. But let's say that it's a bit over the half, so it will take n divided by 2, let's say, but that's still a lot of elements to traverse. But instead, if we could do binary search, that means that, okay, we cut it in half, so we take the start and the end, and then we add them together and we divide by 2, and we get a mid variable, which will be here. And then we look, is this place still valid? Meaning that we will call the is it still valid function, which we'll try to traverse all the way to the end. And if it is valid, if it says, okay, it's possible, then it means that this is okay. It is not cut off. So we know that the cutoff spot is somewhere later. So then we take again the starting value, which is now right this one, and the ending value, and we cut it in 2 again, so half again. And then we check, is this possible? Well, no, because the cutoff point is here, we can say. Then we check again, half this, it's not possible. Half this, it is possible. And then half this, and then we can see that it is not possible. But if this was the last element, then we know that this is the cutoff point. So we know that this index is the place, and then we can just get the coordinates X and Y, or row and column, and then return this, because that's the answer that it wants to get. And by doing binary search, we have log of n instead of n, which is a lot better. So let me show the is path possible first, and it's basically what we've done before, but I've just included everything here into a function. So the directions, the queue, the visited set, and the queue itself, which will do the same things, but we actually don't care about how many points we have. So we can see that we don't have a 2D grid for visited, we just have a set, because we don't care how many points there is at that specific point. We just want to see that we did not visit it. And if we did not visit it, then we add it to visited, and we add it to the queue, of course. So we keep searching, and if there is a case where, let's say that this is the map, if there's a case where we want to get from beginning to the end, but somehow it's cut off like this, then we will try to traverse all sorts of different places. And once we've traversed all of the different places that it's possible, and we've appended all the different ways that we can travel, if we see that somehow any of these places that we added to the queue, if they are not equal to the end, then it's never going to return true. And what it's going to do is it's going to pop each element from the queue one by one until it runs out, and it will run out if it's blocked. And when it runs out, it will just return false. So that's what it does. If it sees that it's sort of stuck or backed in a corner and it cannot get to the end, then it will return false. But if somehow there's a tiny opening somewhere, then it will keep going, and then it will reach the end, and we will get true no matter what. So in this with this function, we just care if it is possible to get to the end or not. We don't care about the price to get there. And the way that we implemented binary search, which we don't have to do, but it's a lot more efficient, is that we have a low and a high value, and the low value is 0, and the high value is how many bytes there are to fall. And we just check mid every time, and we always reassign low and high. So the mid, if low is 0 and high is 100, mid will be 50. So we'll be resetting the grid, so there is no hashtags in it, and then we'll be adding how many hashtags we need, so until mid, so 50 of them plus 1, let's say, and that's how many hashtags we add. Then we check, is this still possible with 51 hashtags? Oh, it is? Then great. It means that we searched too low, so we have to search higher. So we say that now low is equal to the mid value, which is 50. So next time that it will check this, it will check from 50 plus 100. So 150 divided by 2, that's 75. So now the new mid is 75. If it sees that it's too high, then we have to search earlier bytes. So we make high is equal to mid, the current mid. So then we search the earlier bytes, and so on and so on and so on. And if we've gone into this statement, we also save mid as the blocking index, because the last time that this will occur will be the last element that was the blocking index. And once we've run out of options, because we only check while low is less than or equal to high, and we can see that low always increases until mid plus 1. So it will eventually surpass high, and then it will break once we've had one element left, and we will have blocking index. And if it's not -1, meaning that we did find it, then we set it to X and Y, and then we print it as they wanted us to do. And you can print the exact values with commas in between with a F and quotes, or you can just do join comma, that works as well. And they want us they want the X and Y coordinates, not the actual index. That's why we're not printing the index. So if we run this, we get 851. And that is also the correct answer. So now for the time complexity of part 1. What we have is n, the number of nodes processed, and m, the size of the grid, which is rows and columns. And then reading the input, since 1024 bytes is fixed then and independent of m, we can just say that it's O of 1. Initializing the grid is O of m, because that is the entire grid. And then we have the breadth first search algorithm, which has queue operations and direction checks. So what we can say is that the total time complexity of this program is m plus n for part 1. And the space complexity is all of m, which is pretty good. And then for part 2, it's a bit worse because we have to do a breadth first search, but it would have been even worse if we didn't. So it would have been almost n squared, because we have n plus n times log n, but it would have been times n, so n times n becomes n squared. But since we've done binary search, then it's a lot better. So we have the binary search iterations, of course, and we have to reset the grid every time and apply the bytes to the grid and do a BFS check for the path. So if the path is even possible, calling that function, and that also takes all of m to check at worst all of the places in the grid. So the time complexity for part 2 is m plus n times log n, which is pretty good. And then the spice complexity is the same as part 1. It's all of m, because we still store the same variables. When we reset the grid, it's not like we store the old one as well and it keeps getting worse. We just reset the exact same grid. So that was the time complexities. And now if you guys want to join the leaderboard, I will leave the code in the description. And thank you for watching. Happy holidays and see you tomorrow.